Okay, so let's get started. So this is the last lecture of the semester. So we're just going to sort of wrap things up. I'll finish just describing the sort of multi-phase models that are used a lot in internal gun ballistics and dust explosions, things like that. And then I'll just show some presentations that I gave over the years, just that basically demonstrates the use of these equations. And these equations, like I said earlier, are really complicated. They take a lot of, you need to work with them quite a bit to gain confidence with them. And so, and part of the reason that I discussed these the very last thing is that there are all sorts of fun details that I find interesting, and I would get sidetracked. We would be going over these for about 2 months, just because there's so much stuff to go over with them. And I think that would miss the point of this class, and I would fall into that. So I'm not doing that. But anyways, so now we're talking about an equation for a bunch of Eulerian particles that are embedded in the control volume. And then one way to derive these is you can almost think of drawing a control volume around all the particles. Then you basically average out all their properties over the overall control volume. The more modern way to do it is to actually use the Boltzmann equation to derive the governing equations. And if you use that as the most fundamental way to do it, in my opinion, and that does introduce about 3 or 4 extra terms that are not included if you do it the control volume style. But working with the Boltzmann equation is way beyond the scope of this class. And so what we had discussed, what the granular particles can do is that when you do this control volume analysis, you do wind up with a set of field equations that are very much like the Navier-Stokes equations. And basically, you can think of essentially a gas as just a bunch of colliding molecules. Well, you can think of this field of particles as just a field of colliding particles. And so if you take the same concept that you have for a bunch of molecules and apply it to particles, you get the exact same concept. And so the main difference between a gas, a monotonic gas such as argon, which only has, there's only the one atom, and granular particles, is the fact that when molecules collide, there is no energy lost in the collisions, or I should say there's no kinetic energy lost in the collisions, whereas for particles there are, just basically due to a sort of the coefficient of restitution. And so all those effects make granular media actually really sort of interesting and complex. And these collision processes for particles give rise to basically pressure-like forces that if you work in the field of internal gun ballistics, it's called intergranular stress. If you come from more of a traditional granular multi-phase flow point of view, it's called solids pressure. And of course, the other way to tackle the particles is to use a Lagrangian point particle type of approach. And there you solve just a standard set of Lagrangian F equals ma type of equations for the particles. And I'm not going to go over those in basically much more than that, because Bala teaches a really good multi-phase flow class where he goes over that kind of stuff. And also Bala's group is, again, a world-renowned expert on doing those kinds of things. And so, and the other reason is that for combustion, the particles are, as I said before, are very, very small, so that they burn efficiently. And so there's just a huge number of particles. And so that means you do need to be a little bit careful using Lagrangian point particles, is that there'd be a lot of them, and even if even if you do some tricks to reduce the number of point particles, there are some issues with that. But I'm not going to get into those. They are very subtle, and you do see them, and you do see some weird influences of, if you basically say that one particle or that one computational particle is equivalent to, say, 1,000 or say 10,000 physical particles, you wind up with very weird things. Like if there's even one particle in your computational cell, and say it's pure carbon, your equivalence ratio by the sort of random motion of the particles in that computational cell is like 100,000, whereas in the neighboring cells where there may be no computational particles present, the equivalence ratio is 0, and so no one's really dealt with that effectively yet, and so you do need to be really careful. However, where Lagrangian for combustion applications, where the Lagrangian particle methods work very well, are if you have larger particles that are on the order of 100 micrometers to a few millimeters, and you want to track those. They work very well for that. In fact, they're far superior to Eulerian methods for those applications. Okay, so at any rate, we're just gonna wrap up the governing equations, and in addition, there is for the particles, there is a transport of what's called pseudo-thermal energy. Yeah, I know it's sort of a strange term, but what pseudo-thermal energy is it's just the random translational kinetic energy of the particles. It's just given by 3/2 theta s, and it's really the random translational kinetic energy of the particles. It is the exact same concept as the random translational kinetic energy of a gaseous molecule, and so it's the exact same concept. For those of you who've taken some high-speed aerodynamics courses are familiar with it. It's the same concept as the translational temperature for a gas. It is identical to that. Then you have an additional transport equation for basically that term here, and this term here accounts for the fact that if two particles collide, if two particles collide, then that basically reduces this random translational kinetic energy. And so this term here is not present for a gas. It does not exist for a gas, but it exists for particles. And basically this just accounts for the fact that that collisions between particles are not fully elastic. And so where this equation factors in is we derive what's called a granular temperature. It is not related to the normal thermodynamic temperature. It is its own thing. It's just given the term. It's the same concept as a kinetic temperature for a molecule, and basically theta s and alpha s are used in an equation of state for the particles to determine the sort of solids pressure, and this is analogous to the gas phase equation of state, where basically the volume fraction but now the density of the particles is constant. But now in that equation of state, basically you can think of the volume fraction as taking the role of density in a gas, and the granular temperature sort of taking the role of normal thermodynamic temperature for a gas. Okay, and so basically, this is analogous. There is the ideal gas version of the solids pressure isn't very useful. So there's only a real gas version of it. However, the real gas equations of state, or the real gas type of equation of states for the solid particles do not have near the complexity that they do for a gas, just because a lot of the complexity for the equation of state for a gas comes from how the molecules interact at very high pressures when they get very close to when they get basically when they get very close to each other. And for particles, those terms are not present, basically because the particles are so large that those intermolecular forces between the particles are small in comparison to all of the other forces. Okay, and so and then finally there is a transport equation for the normal internal energy of the flow that has convective heat transfer. This is where if two particles collide and you reduce the random translational kinetic energy of the particles, well, that energy has to go somewhere, and it goes into heating the particles, just because you could imagine if you have two particles smashing into one another, there's going to be sort of viscoelastic stress wave moving through those particles, which is eventually going to be dissipated as heat internally inside of the particle. Okay, and so these are the equations for the particles. Are there any questions? Okay, and then finally there are the gas equations, and these are identical to the gas equations that I derived earlier. Okay, and so these are really roughly the governing equations, and now I'll show some examples of how we've actually used those. So let's see. Okay, full screen mode. Oh, well. We'll just have to do it like this. So one application where solving this coupled reactive gas to granular particles comes into play is studying dust explosions. And so these are quite devastating. And a primary example in the United States of a dust explosion is the 2010 disaster at the Upper Big Branch mine. Essentially what the miners were doing, they were basically mining coal out of a seam right here. And along with coal seams, there's a lot of natural gas present. And so essentially when they are mining these, they need to ventilate the area where they are mining very, very carefully. They will, and then when they use their cutting equipment to basically cut into the coal, they need to use very sharp carbide tip teeth that don't throw sparks, and then they also use water jets to basically try to keep the temperatures cool and then also keep the dust down. Unfortunately, for the Upper Big Branch mine, none of those things were present just due to neglect. And so what happened then is the natural gas accumulated, and there's, as a consequence of Murphy's law, if you have an explosive concentration of gas or particles hanging around long enough, it will find an ignition source, and this was no different. So what happened then was there was a natural gas explosion, and that explosion produced a shock wave like any other process. And the explosion radius for that gas phase explosion was this little thing in blue. But the overall damage to the mine was in this giant red region here. And let's see, nope. It was this giant was this giant red region here. And what the owner of the mine was found to be criminally negligent for was, as part of mining operations, there's coal dust that basically gets sprinkled onto the floor of the coal mine, and they're supposed to clean them up, because obviously if you have reactive dust sprinkled all over your coal mine, and something happens, you could basically blow up the entire mine, which is exactly what happened here. So what happened was there was a shock wave produced from the primary natural gas explosion that produced a blast wave that then propagated over the layers of accumulated coal dust, dispersed it into the air, and then that produced a secondary dust explosion. And it's not secondary in terms of importance, it's secondary in terms of order of events. And that secondary coal dust explosion propagated for over a mile and produced the damage that you see in red. Okay, so these things, when they happen, they tend to be very, very huge. And the overpressure for these are basically fairly small in comparison to the energetic materials that we've been discussing in this class. Maybe at most a couple of bars. But you got to remember that the reaction processes for coal dust explosions are far slower than they are for an explosive. And so you could imagine if there's in the profile, which I'll show later, of the profile between the shock and the end of the sort of reaction zone of a dust explosion is many, 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 many meters in length. So there is a huge amount of surface area where the high pressure behind the lead shock wave can basically push on things. And so damage that you see from coal mine explosions tends to be of the form that you see a giant, like 6-inch thick steel door being basically ripped off its hinges and thrown across a room. And that's just basically due to there's a fairly modest pressure, but it's pushing on the entire door and the hinges can't take it. Whereas if you were to detonate a high explosive charge by that door, it would tend to basically punch a hole in the door or maybe shatter it. But it would probably not rip it off the hinges. I mean, unless it was a huge explosive. Okay, and so just basically due to how, basically to the differences in those types of explosions, you see completely different damage. And so there are some experiments that have done at the Brewston mine where they basically mimic these types of scenarios. And so here, what they have towards the end of that, I'll play it again, is you see a bunch of coal dust being ejected out of a shaft. There's a layer of coal dust that is on the floor. They ignite a flame, and then as the flame propagates, like you guys did on your homework, it's basically moving from the closed end of a tube to the open end of the tube. And as you guys know from your from homework 4, that's driving a flow in front of the flame. But that flow, and then that flow is going over a layer of dust, and then it's dispersing it into the air, and then that basically starts contributing to the explosion. And then that entrained dust, most of it in this experiment got ejected out of the end of the test mine shaft and produced the big giant fireball and little explosions that you heard in the video. And so what we are still doing, what Swagnik is doing, is we're trying to understand the details of how these layered dust explosions tick. They're called layered dust explosions because the dust starts out in a layer on the floor, and there are a whole lot of basic physics questions as to what are the coupling mechanisms that allow a dust explosion to propagate for over a mile. How do shock waves and these ground layers interact? That's a very fundamental multi-phase flow question. And then what's the role of thermal radiation? all sorts of questions. And so we use numerical simulations. We basically mimicked the scenario either in the Brewston mine tests, or the Upper Big Branch mine explosion. So we set up a computational scenario where we had a very long shaft here. I think Swodnik has basically this same height for his current simulations, 5 centimeters high. Only his channel is 40 meters in length. These dust explosions take a very long time to set up. And then to trigger the explosion, we have a region on the left side of the domain that is filled with a stoichiometric mixture of methane and air, where we intentionally trigger a detonation. And so basically this detonation propagating through the methane and air mixture functions as the primary explosion, and this primary explosion produces the shock wave and high-speed flow that then initiates the dust explosion. Okay, and so this is mimicking what happened in the Upper Big Branch mine explosion. And so now in terms of multi-phase flow, this is really difficult. We didn't know what to do with the dust layer. And so our only option was to resolve it and actually put it in the computational domain and not treat it as some weird fuel boundary condition. And so this is very challenging. In the highly compacted zone of a dust layer, the particle volume fraction can be 65%, which is the volume fraction of particles that you get if you just take a bunch of spheres, like in a ball pit, and just dump them in. The sort of volume fraction of the balls in the ball pit at McDonald's or something like that would be on the order of 65%, like basically give or take. And also you have this shock wave that'll be sliding over a layer of dust. And so the model has to account for compaction processes that basically impulsively increase the volume fraction of the particles, like I showed in the movie last time. And also in terms of the numerical algorithm, these are challenging computations because you have a very dense granular, you have an interface between air here and a very dense granular layer here, and a strong shock wave basically sliding over that layer of dust. And so that's a very challenging from a computational standpoint to do. And that's actually what I spent a year of my postdoc, was actually just getting that, just getting the algorithm to work. And so, but I won't get into that. If this is more of a numerical methods oriented class, I would certainly feel free to talk about that. Okay, and so let's see, get this. And so the multi-phase model was actually that we used and that I partly developed was actually the ones that I just presented. And so the starting point for this multi-phase model were actually internal gun ballistic. Were basically models for internal gun ballistics that were pioneered by Dr. Coe and Dr. Summerfield. Oh, and in this presentation, it was to honor the life of Ken Coe, who actually passed away a few months before we gave this talk. And so basically this talk was to honor him, was basically given by a bunch of his, was basically a session at an AA conference for a bunch of his former students. And we just talked about basically what we were working on. And so what Ken had developed are very similar. This was in the 60s, and these are precursors to basically modern granular theory. In fact, if you trace the history of the Eulerian granular multi-phase flow models, they use some ideas from Ken Coe and Martin Summerfield, Ken Coe's advisor at Princeton. And so actually modern granular multi-phase flow theory has its roots in internal gun ballistics. And so essentially what basically Ken modeled back in the 60s, or developed these sort of models for in the 60s or 70s, was actually describing the combustion wave of basically solid propellant grains in artillery shells. And those are identical to the granular multi-phase models that I now use for basic coal dust explosions. The differences are that For coal dust explosions or aluminum dust explosions, I use burning rate laws that are appropriate for coal or aluminum. All these here are basically small little solid propellant grains, and so the burning rate, so the burning model for those are basically based on Saint Robert's law with an erosive burning correction factor. So it's an AP to the N with a convective heat transfer influence on them, because as this here over here is the primary, or is the primer. So basically, when the hammer strikes the primer, it shoots a bunch of hot particles into this granular propellant bed, and that ignites a flame, which then propagates through the sort of granular propellant bed. Okay, and so basically, our model is actually has its roots in basically modeling those types of gun systems. However, the models for internal gun ballistics didn't quite work for the coal dust explosion, because we had regions of core flow where there are no particles, and the internal gun ballistic models really didn't care about those regions, so they didn't focus on making them accurate. And so we needed a way to basically bridge those two, basically bridge the region where the particles are really densely compacted, especially after the combustion waveforms and the pressure increases in this little chamber, and also smoothly transition to the region where there are no particles. And so essentially, we started looking into modern kinetic theory of granular particles, and those can account for what are called particle-particle interactions. That's particles sort of colliding. It can account for friction-like effects as particles slide one over one another, which you see on this experimental image here of just a pure granular flow. It's just basically a bunch of beads that have been tipped down an inclined plane. And the interesting thing about particles, about granular particles, is that depending on how they're packed, they can exhibit, and the energy applied to them, they can, basically how you shake it, they can act like solids, liquids, or even gases. And so basically particles sliding down an inclined plane exhibit all of those processes. And so kinetic theory models attempt to basically model at least these two processes here. They don't do very well for the solid-like regime. Although there are corrections to that, they're really complicated to apply, and so we don't use them. Okay, and so I won't get into that. But the governing equations that we use for the coal dust explosion are written right here. They should look familiar because they are the ones that I just wrote down, sans the sort of diffusion terms. And also we did solve a bunch of species mass equations too, but I just didn't write them down because in a presentation, you don't want to pepper the audience with too many equations. And then essentially, then we have a different set of field equations for the granular phase. So this is conservation of mass, momentum, pseudo-thermal energy, and internal energy. And basically, the terms here that are in red are the extra terms that were added to the old interior gun ballistic models that were developed about 60 years ago. And so basically, the model for a coal dust explosion is almost the same as the model that you use to simulate a burning gun propellant in a gun system. And so the only differences are basically you need to consider all of these sort of collisional terms. Although in modern gun ballistics, you could easily basically use these ideas too for those types of models. And so really the only difference in if we were to if those gun ballistic models were to be sort of repeated, would be just the subgrid models themselves. Your choice of the drag coefficient model, you would probably choose something different for that, and you would choose and then obviously a different burning rate model. But other than that, they are more or less the same, and a different equation of state for the gas, because for guns, The pressure gets down to the order of 50 to 100,000 psi. So clearly you can't use ideal gas for those types of conditions. Okay, and so like any other good code study, we need to verify and validate the code. I'm not going to get into that. I just get into the results. And so what we then did is then verify it against experimental data. There were some nice experimental data done in China in 2007, where they took a shock wave, basically passed it over a layer of dust, and they used some X-ray photography and they seeded the layer of dust with basically heavy lead oxide particles. And what was really interesting was that they could actually see the edge of the sort of a granular shock that is transmitted into the dust layer. And when we ran our model, we got in within 0.8 degrees of those measurements. And considering all the crudeness of the assumptions that we have to use for our model, we were very, very happy with that. And then there were some recent experiments done at Texas A&M where they did a similar experiment where they took a shock wave and slid it over a layer of dust. But rather than looking inside of the dust layer, they looked above the dust layer, and basically they were interested in basically how the dust layer, or how the fine layer of dust it basically gets dispersed above the dust layer. And this is analogous to basically the flow, or basically if you've ever followed a car on a dirt road or a gravel road, and it's a dry day, you would basically, there would be lots of dust that is sort of kicked up and into the air. And so a shock wave traveling over a layer of loose dust induces a flow that then entrains the dust into the up into the core of the channel, much like basically much like the wake behind, or basically much like the dust that is kicked up into the air from a car basically traveling down a dusty road. It's the same, it's essentially the same process. And so there have been some recent experiments. And so what we did was we set up computational versions of those experiments. And so we have the shock wave sliding over the layer of dust, and we have the dust layer itself, which we are resolving. And then we have the outer edge of the dispersed dust. And notice the volume fraction of this dispersed dust is on the order of 10 to the minus 4. And unfortunately, the stoichiometric volume fraction of coal dust and air is right around 10 to the minus 4. And so for dust explosions, this is really bad. It just so happens that the volume fraction, or that the equivalence ratio of most fuel layers, or most dust layers that are dispersed into the air, are basically right in the middle of the very explosive regime. And so that's sort of an unfortunate thing. And then we also compared our computational results in these lines here with various modeling assumptions, and then compared it to the experimental measurements. There's a strange shift in the experimental measurements. It's how they presented them, and we to this day we still have not figured out what's causing this shift, because we think there's a subtle difference in how the height of on a reference height, because if we take these points here and slide them down, our definitions, the sort of dust lifting height matches very well with the experimental measurements. Okay. So next, and so now we also verified the code for a whole bunch of flames and things like that. And so now we are ready to go and study and then use our models to study how dust explosions propagate in these layered dust configurations. And so here's just a scenario here. We have a sort of stoichiometric methane air mixture and we trigger a detonation through it. That acts as the primary explosion. That primary explosion slides over the layer of dust, kicks the coal dust into the air, which then subsequently starts to burn and the shock heated air. And these are our very first calculations of this that we did 6 years ago now. Swagnick has updated the sort of reaction model and has started including effects like thermal radiation. And he's seeing different results. We've basically updated the sort of numerical method and model, and how these explosions tick is dependent on the reaction model. And so I got slightly different results back then than Swagnick does now. And so coal dust particles, or even any organic dust such as biomass, they sort of act the same way. Is that you could think of them as one particle. They are never spherical, but computationally you have to treat them as spherical because you don't know enough about their shapes. But you can think of the particles as being a homogeneous mixture of char, which is basically carbon, some basically gaseous volatiles, and then inert ash. And so as the coal particle heats up, it basically vaporizes to produce natural gas, which we are treating as basically methane. Then that methane goes into the surrounding air, where it can subsequently react with the oxygen to form CO2 and H2O. But then after the methane leaves the coal particle, there is a sort of carbon. There is a lot of carbon left over. And then that carbon is also free to basically react with oxygen via a surface reaction to directly form CO2. And so this sort of leftover carbon is no different than the charcoal that basically that you can buy from the grocery store that you might use in your grill. Is basically they basically preheated up the wood, and all the ash and volatiles and tars, which are also present in coal, have basically all been leached out. So what you have nominally is almost almost pure carbon with a bit of ash that is left over. Okay, and so for the simulations, we use basically simplified global reaction rate models based on Arrhenius kinetics. For the devolatilization process, for methane combustion, and then also the carbon char combustion. Okay, and so let's see. So I'll just get to the results. So here, I don't think this will repeat. And so here we have a layer of dust, the shock wave sliding over it, and this here is just a layer of dust. It's just basically the height of the dispersed dust, which again compares well with experimental measurements. And then after a time, then after an ignition delay, for this case, we see a massive coal dust flame basically moving by. So let me play it again. So the shock wave moves by, the dust gets dispersed into the air, which you see right here. And then if you look on the top pane here, which is the temperature, you'll eventually see a flame kernels form. And these are producing acoustic waves, which you see in the Schlieren, and that is producing a carbon dust or a coal dust flame. And Swagnick he basically updated the reaction model, and he sees a different. So he's now seeing a different flame structure. But in either case, you can see there's a really complicated interaction between shock physics, a multi-phase flow, particle dispersal, and combustion. And so, and these all sort of conspire to produce these interesting dust explosion results. And so this sort of flame structure surprised us, and we basically scoured the lit, and we did find some evidence of that type of flame structure. I'm not going to get into that. But anyway, so what we learned, our big take home for a layered dust explosion, provided the shock is strong enough to ignite everything, is that basically, at least for the conditions that we simulated, you can sort of think of a self-propagating explosion as and basically we call them a shock flame complex. It's not a detonation, even though it's a shock-induced combustion. It is not a detonation. because the shock and the flame are not moving together. The shock is moving faster than the flame. And so what happens is you have the shock that's sliding over the layer of dust. There's a fine layer of dispersed dust that gets kicked up into the air. Eventually, through either normal flame processes or auto ignition processes, a coal dust flame ignites. Those produce acoustic waves, and those acoustic waves then propagate forward, and then push on the leading shock. And eventually, what happens is you wind up with a self-sustaining, basically coal dust flame. And this is one mechanism of them. I'm sure there are many, many, many others. Okay, so are there any questions on this work? Okay, then some other stuff, a bit more energetic-y. Slideshow. Oh, and I'm going to stop recording because this isn't published yet.